So in the last lecture I gave various properties of the unitary group of 2 by 2 matrices, the group which is commonly called as SU2, and I gave a particular basis for writing down these 2 by 2 matrices, and it's very easily defined, but there are lots of reasons for choosing this particular basis, and that is the nice properties. I will write them down explicitly what they are. So this is a complete okay. What is the meaning of this word? Complete means any 2 by 2 matrix can be written as linear combination of this. Okay, it's a standard label for linear algebra. What does orthonormal means? That the various components in this basis are somehow perpendicular in the sense that they have zero overlap. Okay. So overlap, you know how to define for vectors. It's just like a dot product, and whether it is a 0, that means they are perpendicular. But these are matrices, so there is a corresponding overlap or inner product for matrices. Which is defined as multiply the two matrices, one of them is conjugated, Hermitian conjugate, and then take a trace. Fan is making noise. All right. That's fine. So for vectors it was just V1, this conjugate V2, and that gives a number. Okay. For matrices, if you do the same thing, you will get a matrix, but then you take a trace. So this is a standard, again, definition taken from linear algebra, and if you do this with Pauli basis, you will immediately see that the 4 matrices obey these particular properties. So having this structure in any linear algebra platform is quite convenient. It's a generalization of what you do with Cartesian coordinates, and you can do it with 2 by 2 matrices in a very simple manner. There is another property is that these sigma mu are both can be easily checked. Hermitian, which you take these conjugate transpose, they go back to itself, and they become unitary because the square of them is equal to identity. So Hermitian conjugate is the same matrix, square is identity, so both these properties are simultaneously satisfied. So these are all very easy to check properties, but they are also very useful. And Yeah, I can add something more that I only talked about the unitary matrices last time, but you can also list the properties of 2 by 2 Hermitian matrices. Since this is a complete basis, you can write it in this basis as well. But let us start at just a brute force kind of thing, that I will write say a matrix alpha, beta, and the Hermitian nature will then tell me that transpose element is complex conjugate, and there is nothing I can say about the third one, whatever it is. So how do I write it in the Pauli basis? Well, you have to do simple calculation. This identity and sigma 3 are diagonal, so I can write them as this particular combination. So remember, I is the two elements are 1 on the diagonal, sigma 3 is 1 and minus 1 on the diagonal. You add this thing up and you will get this alpha and delta in the correct place. What about this? They can also be written as real part of sigma 1 and the imaginary part changes sign, but the sigma 2 already has the imaginary value sitting on the off diagonal term, so it just looks like this. And now note that these are all numbers which are real numbers. I can relabel them and I can write this thing as a four numbers. B0 is the coefficient of identity, and these other three are absorbed in these vectors. And this structure, now if you remember what was the analogous thing for the unitary matrices, the difference is a factor of I in front of these Pauli matrices. But this is again completely general. I have not put any restriction on these vectors B because the norm of these Hermitian matrices are not constrained in a particular way. But if you look at last time, the unitary matrix had a structure A0 times identity plus I times A dot sigma. And this I, in some sense, represents a phase, which is there in the unitary matrix and not there in the real matrix. And there are lots of powerful results from linear algebra which express these quantities in different ways, and maybe I will just quote them without any proof. That is all right. So all this was two-dimensional, but you can ask what are the generalizations for arbitrary dimension, and they can be proved. So unitary matrices, these are I was writing some notation. Okay, let me just write U dagger, U is identity, and Hermitian I will write just H dagger is equal to H. What does linear algebra results tell you? They tell you about transformations and eigenvalues and eigenvectors and all those kind of properties, what is the basis, etc. So what are the corresponding properties of this? So okay, I will write little table that probably. What are the eigenvalues of this object, and all the eigenvalues for any unitary matrix have unit magnitude. It is a phase. So that is the understanding. We saw simple examples, but this is a general statement. And what is the situation is, in this particular case, all the eigenvalues are real numbers for Hermitian matrices. What about eigenvectors? Well, part of it is already buried in when you're trying to prove that, but you can easily derive that as well. And in both cases, you can find the eigenvectors as an orthonormal basis. Remember, eigenvectors, you can fix the normalization, that is why you can make it a unit magnitude if you want, but in both cases you can find the eigenvectors and show that there is an orthonormal basis for those particular vectors. The eigenvalue problems are also connected with taking these matrices and transforming them to a diagonal basis. So that is how you find the eigenvalue in the standard linear algebra exercise. You take a matrix, you diagonalize it, and then the diagonal values are the eigenvalues, and the diagonalizing matrix gives you all the eigenvectors. Okay. So that is again in both this situation. You can diagonalize these matrices by a unitary transformation by writing it down explicitly. I can say that what is a unitary transformation? I can write the formula. So U is equal to V times phase. It's not the same V, so let me just write V prime. Where V over V this is a diagonalization operation for linear algebra. A matrix can be transformed. Transformation appears as a unitary factor before and a complex conjugate transpose factor on the other side, and then I can find a V such that whatever remains in the middle is diagonal. So for unitary matrix, this diagonal part will be phases. For the Hermitian matrix, the diagonal part will be all real. These are very simple exercises, but you can prove it in your spare time. They don't take more than some 3-4 lines of proof. It's not very complicated at all. But there is another way of expressing this result which gives you some insight in what is going on. So any matrix can be expressed as M is equal to U times H, or you can write it in the other order. It will not be the same matrix, but some other matrix as a product of a unitary matrix and a Hermitian matrix. What is the significance of it? That this is a generalization of what you know for complex numbers, which is any z is equal to r times e raised to I phi. There is a magnitude and there is a phase. So the unitary matrix represents the phase and the Hermitian matrix represents the magnitude. One can ask that I didn't make the magnitude always positive, because Hermitian matrix only tells you that the eigenvalues are real, it doesn't say they are positive or negative. But that is kind of trivial. In this product, you can take that negative sign and combine it with the corresponding part in the unitary matrix. That is fine. Negative sign does not change the unitary eigenvalue. If a mod is 1, flip the sign, that doesn't matter. So in this case, the h or h prime can be made positive in addition to being real by some redefinition of what is contained in the unitary matrix. And then it is perfectly okay that it's a positive number multiplied by a phase. And this understanding turns out to be very useful in doing lots of manipulations in linear algebra. Unitary and Hermitian matrices play a very important role in all kinds of things which we do. Okay. So if you have not seen any of this kind of thing, it will be good to go back, think about the arguments and work out some of those results. I will state a lot of things over here, but ultimately you have to figure it out yourself at least once. Okay, you may not have to repeat every time you want to do, but once you check that yes, it works, then you can use the standard results all the time. So it's some homework exercise for you. Okay, so this is all kind of things which are very useful for all things which we will do in transformations. This unitary and Hermitian matrices are going to play a lot of roles in quantum theory. There was one more thing which I introduced, but not in the context of group, and that was the state, physical state or a vector. Okay. So on which this matrix is going to act. So I had this equation, something of this type, which I used to construct that when the norm of this vector is constant, preserved, this is a unitary matrix. I wrote down this last time, and one can now try to understand what is the geometrical description of this two-component vector. Okay. So one thing is obvious from this equation itself, that if I multiply psi by a constant means just a number, the psi prime will get multiplied by the same number. It goes through the matrix. The number doesn't bother about commutation, anti-commutation. The same constant will go on the other side. And that property is useful in fixing the normalization of the vector. That if it has some normalization, psi prime will have the same normalization. Now normalization again, you can choose, there is a magnitude, whatever that constant multiplying it, and it is also a phase. But both of them go through, no problem. Whatever that complex number, maybe if I multiply psi by some factor z, psi prime will get multiplied by same factor z, and so that overall complex number is not going to be relevant, and we'll fix it. Okay, so by some convention. Okay, and I will take it to be 1 for simplicity, no problem. And now I will ask, what is the geometrical picture I can construct? Again, I will write two-component vector, complex numbers, alpha and beta. What can I say about these numbers? Okay. So one thing is say that if I fix this normalization, so I can choose the inner product of itself, which defines the norm, equal to 1. I was using the same notation over here, but there were many more numbers. In case of unitary matrices, here there are only 2. And then it's very easy to parameterize this in terms of trigonometric functions, because we know this cosine square plus sine square equal to 1. So I can reduce these two numbers to one angle, whatever it is. And so what does this then look like? Most general form says one magnitude is a cosine, the other magnitude is sine, and I will deliberately put the angle to be theta by 2. Okay, the meaning of this half will soon become clear, but it's a magnitude, so theta by 2 is between 0 and pi by 2, the first quadrant of the angle, so theta is between 0 and pi. Okay, that is the reason for putting this angle, so the range is 0 to pi. That has a geometrical meaning, so we'll see that. And now there are phases, 2 phases for these two numbers. I can factor out one of them, because that will be a common phase and it will go out in the normalization. So I can write this as e raised to I times theta is already here. Let me put delta. Okay. And then there will be a one relative phase, which I am going to write at e raised to I phi. This one, both are there in this complex numbers, but this will disappear by some convention where you factor out everything. And the linear algebra, again, notation is whatever is sitting outside, if you multiply it to a matrix, it multiplies every element of the matrix. Okay, so if I put e raised to I delta, it will look like e raised to I delta times alpha and e raised to I delta times beta. That's how the products are defined. And so this is the most general parameterization. And this parameterization can now be used to give a geometrical picture which will tell you why I choose this particular notation. So if you remember the three-dimensional polar coordinates, these are exactly the ranges of those coordinates. The theta is angle from the north pole, it goes from 0 to pi as you go to the south pole, and phi is the rotation angle about the vertical axis, which goes from 0 to 2 pi. So this whole stuff, this is outside phase which doesn't matter, so it can be represented as a point on three-dimensional sphere, and the notation for that in the geometry is S with 2. The 2 refers to the number of parameters of the, this is a unit sphere. Magnitude is 1. Yes?
So in the first or second column, the entry, why have we written anything?
By?
In the matrix, the first or second column,
Yeah.
there is the entry.
This is not a matrix, it's a two-component vector.
Oh.
This is a product. A complex number. So remember, this is slightly different than what I got for SU2. SU2 I also got a sphere, unit sphere, but it was in 4 dimensions. This vector is again a point on a sphere, but it is in 3 dimensions. But it is a geometrical picture which is going to be very useful, and then all the transformations which is this. They are nothing but rotations in 3 dimensions. Because all you are doing by this transformation is take one point on the sphere to another point on the sphere. And that can always be written as a rotation about some axis. What that axis will be depend on all the parameters of this unitary matrix, and because it is in 3 dimensional, I have 3 axes for performing these rotations, and those 3 axes will map to these 3 Pauli matrices. It's a very nice geometrical picture, and we'll make use of it. Right now, Well, I will give a definition, we can work out the detail later, because it's again a very general property, something similar to the equations which I have been writing down here, that any unitary matrix which is continuation of this, it can be written as exponential of a Hermitian matrix. It follows from this notation, because the matrix is unitary, this magnitude is going to be 1, and what remains is only the phase. And what is the phase? You have to play around with this notation little bit to understand that it can be written as exponential of a Hermitian matrix. And this is something which is again a generic result heavily used in a subject called Lie algebra. But it's a very convenient parameterization, and it allows you to do lots of things very easily, that if you multiply two matrices, they will have some factors like this, so then you can add the Hermitian matrices in the exponent, which is easier than doing a multiplication, etc., etc. But in this particular case, we have a 2 by 2 system, where I can write the result much more explicitly. What is this vector which will perform this rotation? So I can write u is equal to e raised to I, and any Hermitian matrix I can expand in this basis, because it's identity times Pauli matrix combination. So I can write in that, let me just, this is a phase, so it doesn't matter. And the overall phase can be taken out, or doesn't matter. What is important is the stuff which is left over here. In particular, this is a unit matrix which has a norm 1. So this B turns out to be a unit vector. This after specializing to the 2 by 2 case, and this can be written as again a convention. So I think the convention is writing it a minus sign. Should I use the same? We'll derive it explicitly later when the need is, but I wanted to illustrate this picture, so this is convenient, where theta is the rotation angle, and this n is actually it is theta by 2, which is commonly used, consistent with this notation. So this gives an example of the statement I made that any transformation is mapped to rotations in 3 dimensions. What is that rotation? It says n is an axis of rotation, theta is an angle around that particular rotation. And this is the nomenclature which is used. We'll see these things much more explicitly later, but right now I just wanted to complete the description so you have examples of what happens in general and what is a particular case in 2 dimensions. Okay. Yeah. Anything else in linear algebra? Oh yeah, one thing, which is again we will define functions of matrix. Functions of a number is straightforward. You just write f of x and you understand what that means. It's a map taking from x to some other value y, and x and y are numbers, so I can draw some arrows and explain it. What about a matrix? How I define a function? It can be, say, power, it can be exponential, it can be sine, cosine, log, all kind of things. But matrices, I don't know how to calculate those functions because the argument is not a number. So the easiest definition to understand what this is, that these are defined by power series expansions. For example, I wrote down this over here. Nobody asked me how do I exponentiate a matrix. Okay. So the way to understand is, you know the series of exponential, it is 1 plus x squared by 2 factorial, x cubed by 3 factorial, etc., etc. Write down that series and you know how to calculate powers of matrices. No problem with that. So whatever comes out from the evaluation of that series, that is the value of the function. It's a straightforward definition, but you have to give a proper definition. So now I can ask, let us just exponentiate this quantity. I wrote down this expression. What is the value when I calculate the power series? So power series, in this is a number, doesn't matter, but it involves powers of this object, Pauli matrices. And we know that the square of the Pauli matrix is 1. So now I can explicitly ask, what is this object? You can evaluate in many different ways. You can write it as n1 sigma 1 plus n2 sigma 2 plus n3 sigma 3, square the whole thing. Then you expand it, it's a 3 numbers, whole thing square, so you will get 9 numbers, but you have to use all the nice properties of Pauli matrices. If you get sigma 1 square, sigma 2 square, sigma 3 square, it is 1. And sigma I, sigma j, when I is not equal to j, they anti-commute. So you will get cross terms, and there n1, n2 multiplied by sigma 1, sigma 2, and again n1, n2 multiplied by sigma 2, sigma 1. So n1 and n2 are numbers, they commute, but the other two anti-commute, the sum is 0. So if you do this, you will just get these all things are 1, and n1 square, n2 square, n3 square, they are component of a unit vector, so that is equal to 1 as well. So this is equal to identity. So now I expand this. Because of this, all the odd terms can be combined together and all the even terms can be combined together. And when you expand a exponential with I, well-known stuff over here, what is the meaning? It is cosine phi plus I times sine phi. The complex number identity. Same thing repeats over here because of this property. All the odd terms will combine into sine and all the even terms will be combining into cosine. So this is equal to all the even terms. This gives me cosine, and this I will survive. One factor will remain whenever there is an odd power. The other factors will go away by this. So this is an explicit realization of what we mean by exponential. You can write it as straightforward combination of matrices using only addition. And again, this is a simple identity which is very useful in many calculations. Okay. So with all this mathematical machinery, now I can give the definition of quantum dynamics in an axiomatic form. Okay. What do you mean by axiomatic form? This is the way we convert science into technology. Science is developed by making lots of observations, then constructing a theory which will fit all the observations, and then summarizing that theory in terms of a set of rules or laws or whatever you want to call it. In technology, we take those rules as given, and then we design various things according to those rules. Okay. So in the subject of quantum technology, we are going to do that. We are going to accept the rules of quantum mechanics as given. And they are the axioms. And based on the axioms, now we will construct various things which can be done, how it can be done, etc. Now if somebody comes and discovers something more, that one of the rules is going to be modified, then I have to repeat that whole exercise again about what can be done, what cannot be done, etc. It's just a parallel of why we are doing this quantum theory, because we had a classical set of rules. Some things work, but then something did not work. So now I want to replace those classical rules by a set of quantum rules. Again, work through the exercise. If somebody comes and replaces those quantum rules by something else, well, you will have to do the exercise all over again. But that is a way technology works. So this is something which I am going to call axiomatic and it can be very easily summarized. There are not too many rules. It's just that what are the consequences of the rules, we haven't figured out all of them so far, and that is why we are playing around with many things in the technology. So there are 4 different objects we need for this axioms, and I will just write them down one by one. So first object is what are the states that we are going to deal with. I gave an example over here, but this is now going to be more general, and this whole stuff is defined in this language which I mentioned last time for linear algebra. Which is a vector space with this inner product defined as a generalization of the dot product in real space. It's a complex vector space which is called a Hilbert space, and everything will be defined in this. So the states are denoted by this same symbol. So this is a unit ray in the Hilbert space. I will just write with this particular symbol, which is quite common, that this is what it is. I use a different word here, which is called a ray, and it is a vector, but vector is something which we understand from linear algebra and Cartesian coordinate, etc. This is a complex number or complex coordinate space. You can do the same thing and use Pythagoras theorem, etc. to map, but there is one thing which is unnecessary and which is discarded. Even though in the definition and calculation in linear algebra there may be a phase which may be present, it is something like this. I wrote down a common phase overall, but it can be discarded by convention because it goes through everything, doesn't affect any calculation at all, and that overall phase, if you take it out from the vector, whatever remains, you call it a ray. And this is true. I mean, why the physics is like that? That is a phenomena of nature. I can't do anything with it, but all the experiments which we carry out cannot observe this overall phase. That's why it's just understood that we'll throw it out of the theory. What we can observe is a relative phase. And that phenomenon called interference, which is familiar with wave dynamics, you have two signals, but if they have a relative phase, I can see the oscillation pattern, and from that I can find out what is the magnitude of the relative phase. This is an example of that relative phase. The relative phase between here and here, and I can observe it. But this global phase, which goes outside, no experimenter is able to observe it, and that is the definition we'll accept for this state. So it is true that we are doing this kind of definition for convenience, because there is a phenomenon which will use just like interference, that superposition is something which we can very easily do in a vector space. So we will take two signals, you can add them, and then some overall phase comes, you can throw it out. But if you take just two arbitrary vectors and add them, you have possibility of getting arbitrary overall phase. Whatever it is, it's a and that is the reason for going around this thing in a slightly convoluted way. That we want to be able to do superposition, because all the linear algebra is addition of various components, which is nothing but a superposition in a certain sense, and that becomes very transparent once you take the convention that I will introduce some overall phase, do all the calculation, and at the end remove it when the question of measurements or observation comes. So these are going to be all the states. Then there are going to be operators. Operators are matrices which act on the states. And there are going to be two kinds of operators. One is the unitary matrix like this, which defines evolution, and other is observation of some property which is given in terms of a Hermitian matrix. And I will separate the two. So any physical quantity which you can measure from these states will correspond to a Hermitian object, and that is again a fact of nature, and I wrote down here that the Hermitian matrices have real eigenvalues. So what you get a reading on an apparatus is a real number. You cannot get anything else. You can ask, here you are measuring the interference phase. But what you actually mean by that I can evaluate this phi, can measure it in an experiment. But after all, phi is also a real number, connected to the fact that it's a e raised to I, but whatever is sitting here is a Hermitian operator. So all the physical observables are defined by Hermitian matrices. That's it. Nothing more than that. Then there is a third label, which is kind of peculiar in case of quantum mechanics, and that is what happens when you try to measure a particular state. In classical physics, this thing is trivial. That if I have some system sitting at some coordinate x, I measure by some instrument and it will tell me what x is. But here, the system is defined by some psi, and what you are going to get as a result of measurement is a real number. And the two have to be connected. And here is a description given by von Neumann. It is known as a projection postulate. I can here write down a very general form, again comes from the linear algebra, which I said in words over it. What is the description of a generic Hermitian matrix? It can be written in this diagonal form, that it can be some real number, and this matrices are described in terms of eigenvectors, and they are all orthonormal. So the identity which can be expressed is something like this, where I is the eigenvector, and the reverse order comes that this is what you call outer product, not the inner product. And if you multiply a column vector by a row vector, you get a matrix. And the index is the same because the basis is diagonal. I have reduced it to the diagonal basis, and there I can write it as eigenvalues, and these are the eigenvectors. And this is again something which you should understand properly. This is a notation which has a name in linear algebra. It's called the spectral decomposition. So this matrix is there. It has some properties, the observables, the eigenvalues and the eigenvectors I can easily write down. So what does this projection postulate tell me? That observation of some state psi with operator H gives the result I, or well, it's both eigenvector and eigenvalue, so I have to write it more explicitly. The number which appears on the measuring instruments is the eigenvalue, which is real in this particular case. So multiple things are involved. The result on the apparatus is lambda I. The state changes. It no longer remains what it was. It becomes the corresponding eigenvector. And then there are many eigenvectors, so you get a probabilistic description that how often I will get this eigenvector. Well, it is the overlap of the state with the eigenvector in the usual Pythagorean norm. And yeah, one thing is implicit again by the definition of this orthonormal basis, that these are all notations. Just look at this thing. It is called a projection operator. And it has nice properties, which is what is meant by projection operator. If you square it, you get back the same result. That follows from the definition of this orthonormal state. Square is multiplied by same thing, but I contracted with itself gives you 1. And if I sum over all the projection operator, I get identity. This is just what you call Cartesian coordinate analog, that I can take a nice orthogonal basis, for example, in 3-dimensional XYZ coordinates, and I can write the corresponding coefficient, and what the vector is a unit vector. After doing the measurement, sometimes I will get some x, y, and z. How often I will get x, y, or z? It is defined by the Cartesian component of the unit vector, and all those different components, if I add up, it is equal to the length of the vector, which is 1.
Sir,
Yeah.
post measurement of the state is I. Just after the measurement, time is not involved there.
Yeah, the state changes as a result of measurement. It doesn't remain the same.
Time is involved, then it again come back to the side state.
It doesn't come back to the state. This is a irreversible process. And in the language of computer science, information is lost. If you measure, say, in the Cartesian coordinate, a three-dimensional vector, you can get the final component pointing, say, along x direction. But then, what about the y and z? That's gone forever. You cannot recover it. So this is an irreversible process which appears in quantum mechanics. We observe it in experiments. We don't fully understand how it happens, but it happens. And I'm writing down again in the spirit that this is an axiomatic framework. These are the rules. It's an open question, and maybe technology will develop to figure out what is really going on here. But our sophistication has not yet reached that stage. So it's an open question. Okay, my time is up. I have to add one more thing, and that is the last axiom, which is the time evolution of the state. And that is given by the equation written down by Schrödinger. Equation is very simple. The time derivative of the state is given by an operator acting on the state, and this operator is called the Hamiltonian of the system, and it is always Hermitian. And the equation is simple enough to write down the solution. Now I will put the time explicitly. It's just a first order equation. The solution just involves exponentiating this object, and by these rules which I gave here somewhere, H is Hermitian and the exponential is going to turn into a unitary matrix. So this stuff is a unitary matrix, and it is just this particular form which I wrote down earlier. One can ask again how you are going to construct this exponential. Well, define it a power series. But again, even there, the life can be more complicated, that this depends on time. So how do I define a time-dependent exponential? Well, it's defined in the usual sense which we do the integral. We do it by delta t, then the next delta t, the next delta t, and add it all up. So here, since it is an exponential, I will take first delta t, then the second delta t, whatever comes, will multiply that first factor, then the third delta t will multiply the first two factors, etc., and write this unitary matrix as products of this little delta t matrices. So this has again a mathematical label. It is called path ordered product. That means I have to rigorously write it in terms of little delta t steps if it is required. There will be many problems where h is a constant, doesn't depend on time. And then I don't have to worry about this. There can be problems where h depends on time and then you define this product. So this completes the quantum mechanics definition, which is needed to describe all the machinery which is needed in quantum computation or anything else, or in the quantum technology as well. And the job is to understand this framework in more and more detail, which I will do in the succeeding lectures. As far as the definitions are concerned, there is nothing more. But the consequences are, well, unknown. We have to explore it, see whether there are new properties and whether they can give rise to some new phenomena which can be useful.